This video is to teach the step feedback control with integral. So as we understand about the step feedback control before, it is a very straightforward design using the state space approach used to improve the performance of a system. Then today we are going to learn one more improved type of the step feedback controller, which it will be used to reduce the steady state error. How to say this is examples, like when we have a system, after you have designed the step feedback with it, you evaluate the performance, the compensated performance, and you found that the system is still have a huge error. So at this time we need to improve, because we need the steady state error is huge, so the accuracy is low. Then that's why there is a second type of controller, which we call it step feedback with integral. The main reason is to reduce steady state error. So from here we can see this block diagram. The shaded with the pink color line is the added part to our existing step feedback control structure. So from there we can see that before that step feedback, we have the step feedback, we design the K for each of the state variables of the system. So because of due to the high steady state error, so now we would like to truly observe what happened at the output, so that we can reduce the error. So that's why in the new control structure, we feedback the outputs, the major output, and then we compare to our reference input. So we take care of the error, which is the difference between the reference input and the major output, and we use this integral method where we integrate it and then we multiply it with a design gain before it goes to as the control signal to our system. So the integrator will increase the system type and also reduce the steady state error at the same time. So let's examine again the same block diagram. So where we see the new control structure, besides the existing state variables of the system, now we have another state variable, which we call it xn. So why that happened? Because you see in the integral we have one integrator here. So in fact this also is the, if this e equals as the xn dot. Okay, so this one is the dE or dt. Okay, so from here we can see that x dot and y, this is the original one, and then the xn dot, which is this is xn, so xn dot is here, so same as the e, and then the equation of it is the minus c, because it's feedback. Here is the cy, so r minus cy as gx, sorry, this one c, and then we reply here is a y. Okay, so from here we can see that these two step variable. So u equals to, now our u already enhanced to different. Before that is only the substitute to our a minus bk. So now we have a new control law. So when we substitute the control law to the equation 1, then we get this equation ax plus b u, this u, so you substitute it into here, then you can get the equation 3. So continue this slide, we rearrange the equation 3, then we get the equation 4. So we just make the ox at the same together, and then this xn. So now we know that our xn dot is e, and then is these equations. So we rearrange the equation 4 and equation 2 just now. we found this new vector matrix for our step feedback with integral. So from here we can see that to design this controller, we need to obtain the value of the k and also ke. Okay. This is arrangement of the this, because we need k and ke. When we rearrange this equation into the new vector matrix, you will find that our matrix A becomes a enhanced model. Okay. So let's try one example. Design an integrated step feedback control for the plant where we have the phase variable form state space for the plant. Now we need to achieve the 10% overshoot, peak time of 2 seconds, and also 0 steady state error. So we were informed that the open loop 0 is happen at -4. Okay, so same as the procedure to design the step feedback, first we need to get the desired characteristic equation. So based on the given one, the overshoot and the set peak time, so we can do the calculation, substitute to the formula, then you can get these equations. Okay, so characteristic equation is s squared plus, because this zeta omega you substitute in here, then you can get these equations. So back to the question, you can see that in fact it is a model is 2 by 2, although it's 2 by 2, but we know that if we want to design the integral step feedback with integral, our model must go to one more order, means 2 plus 1 is become 3. So now we need to add the third pole at the -4, because that is the value of the 0 to cancel the open loop 0. So you multiply with 4, then you can get the 1. Okay, like I explained just now, this is the integral step feedback with integral. You see you have x, you have xn. Okay, although your system model originally is 2, like this case, second order, okay, but because the control structure, the block diagram you refer just now, we have one extra variables because the system type will increase. So then you must 2 plus 1 becomes 3. That's why just now your desired characteristic equation becomes 3. Okay, so this is what we should get. And then now we need to find out this. The position is A11. So I just use from the question A and then the B. The K is 2K because the model is 2 by 2. So K1, K2. So until here, this step is still same as the step feedback if you found that. Okay, so you do the calculation, then you get this A11. So BKE, now how to get it? BKE is your B. This is from the question. KE is only single. So you multiply. This one is 2 by 1, and then in 1 by 1. So you will get is the 2 by 1, right? So then you try to get it, is the answer 0, 1. So it's a 0 KE here. Okay. So A21 is this one. Okay. Very easy. Your C, just now our C, and then you just multiply with the negative. And then the last is 0. So now you put inside, then you can see all these are the value you have calculated just now. So you got a vector matrix for the step feedback with integral. Now from this new A, you already get the new A here. From this new A, you do the determination. But before that, you need to give the identity first. So that's why S this, then you get the answer. Okay, you get the answer and then you solve it. So you get this characteristic equation. Then you compare the equation 1 from the step 1 just now and this equation 2. Then you can get the value of K2, KE, K1, and so on. This is the final answer. Thank you.